Hi and welcome back. Today we're going to be introducing the application of redox reactions to the formation of electricity. So this will give us an introduction to galvanic cells and the vocabulary associated with them. So we by now have hopefully bedded down the idea that the reducing agent causes reduction by donating its electrons to the oxidizing agent. Okay, so the reducing agent is oxidized and the oxidizing agent is reduced. So we can always follow this by looking for the species that has lost electrons, which will be oxidized, and the species which has gained electrons, which will be reduced. If you think back to the demo that we looked into in class where we placed the copper wire into a solution of silver nitrate, and then from that we saw the silver solid appearing on the wire and eventually the solution turning blue, we can understand what's happening at the atomic level by considering the particles that are in solution and the processes that are occurring. So inside the silver nitrate, we have ions of silver and nitrate, which will be dissociated within the solution. So they're moving freely around as Ag plus and NO3 minus rather than a complex in solution. They're sort of separate. This means that as the copper is oxidized, we are going to be taking copper solid and losing the copper ions off the surface of the copper. And as we do, there are electrons on the surface. These electrons will attract the silver ions to them, and the electrons will then reduce the silver. As it reduces, it sticks to the surface of the copper, and we get the buildup of the silver around the piece of copper wire. So if we think about this, we've got the movement of electrons, and we have the production of energy because redox reactions are exothermic. Okay, they actually generate heat. They're generating energy while they progress, and this is a chemical potential energy to heat energy when they occur in the one flask like this. So this is a spontaneous reaction. We didn't have to do anything to make it happen. At room temperature, the activation energy is such that the reaction will just proceed without any catalyst or anything like that. Okay, so it's spontaneous and it produces heat, so it's exothermic. If we were to separate the two half reactions into separate beakers, though, that is to have the oxidizing agent, to have the oxidation half equation in one beaker and the reduction equation in another beaker. So if we think about this, if we have copper solid with copper sulfate solution and then silver and silver nitrate solution into here, they can't react. But if I join them by an external wire, now the electrons have a conductive medium, those delocalized electrons in the wire, where the electrons can actually move along and get to the other half equation. Okay, these electrons being forced to travel along the wire generates an electron flow or a current, and what we have is electricity. Remembering that electrons will flow from the negative to the positive side, which means in this case, our electrons will be flowing from the side where they're produced, our oxidation reaction, to the side where they are consumed, our reduction reaction. So if we do this, we can actually observe this in electrochemical cells. Okay, so this electrochemical cell idea is where we take redox reactions, make the electrons pass through the wire in order to see a chemical potential into an electrical energy conversion. This gives us evidence for electron transfer because if we take a test tube and place it between a piece of zinc and copper sulfate solution, copper is deposited on the zinc and the solution loses the blue color over time. Okay, so if we were to place a zinc electrode into a copper solution, we're going to see this reaction happen. So by separating these with a glass wall in between them, obviously the electrons can't flow through the glass. We split the two half reactions, insert a light globe or a voltmeter in the circuit, which is what this is indicating here, and observe what happens. The reaction will produce energy that we can harness because it's spontaneous, and because the electrons are going to move through the circuit, then we will see electricity being produced. The light globe will glow. We refer to these type of cells as galvanic cells. Okay. Sometimes you'll see them being referred to as voltaic, but they're exactly the same thing. So voltaic versus galvanic, same thing. So if we have a look at this one here, we can see that we have zinc as the electrode, zinc metal, and the electrode needs to be a conductive piece of solid. Then zinc ions in solution. So this could be zinc chloride or zinc nitrate. We're mainly interested in the net ionic equation, and it's only the zinc ions that we're actually interested in here. This is our electrolyte. Okay, it is the solution that will conduct the current. And then we have the internal circuit, which is the salt bridge, which will be made up of soluble ions, which we'll talk about a little bit later. And the other one, we have our copper solid, and we have a probably copper sulfate solution in here in the electrolyte. So we know that zinc is a more reactive metal. So I can have the displacement reaction, okay, where zinc is a more reactive metal. So zinc will react with copper 2+ to form zinc 2+ and copper solid. The more reactive metal being the reductant and giving its electrons to the less reactive metal. If we pull this apart into two half equations, we can see that zinc solid goes to Zn2+ aqueous plus 2 electrons. We're losing the electrons, so this is oxidation. Our copper ions, Cu2+ aqueous plus 2 electrons, will go to copper solid, and this is our reduction reaction. So these two half equations being placed into two different vessels and then connected by an external circuit or wire, this one here, gives us what we call a galvanic cell. So we need a two redox half equations in the half cells that will spontaneously react, connected by an external and an internal circuit. So in order for the electrical work to be done, the electrons need to travel through the external circuit. If we just placed zinc in a solution containing copper ions, we would see the spontaneous reaction. It would be exothermic, but all we would see would be an increase in heat. So what would generally happen is the zinc rod will be eaten away as the zinc 2+ ions dissolve into solution, and we would see a precipitate of copper forming on the bottom of the beaker. So the oxidation reduction reaction would still occur, but because the electrons are all able to transfer readily without passing through a wire, we won't see any electricity being generated, we'll just see heat. So as I said before, this is the standard setup of a galvanic cell. This is the Daniell cell. The Daniell cell is the copper zinc cell. It's a standard cell that we tend to look at a lot. So in the first beaker, you're going to have your electrolyte solution and the matching metal. So these are your redox pairs. Okay, so this would be your conjugate redox pair for one of the half equations. Okay, this will then be attached by the external circuit wire with a galvanometer, so measuring voltage, or a globe in the circuit. And we must always remember to put this in our circuit when we draw them. Down to the other half equation, so the other redox pair. Okay, remembering this is our oxidation pair. So we have the zinc strip, and in this case, zinc chloride solution with our electrolytes. When we draw them, we need to make sure that the salt bridge and the electrodes are always shown to be below the surface of the electrolyte solution. When we look at how the Daniell cell works, we can see that the zinc is being oxidized from Zn to Zn2+, remembering it's the more reactive metal in this case. So this is where oxidation has occurred, and this is the anode. Okay, so the oxidation always occurs at the anode. Okay, so, and is the negative electrode. Then you may have heard me say red cat. This means that reduction always occurs at the cathode, and in a galvanic cell, the cathode is the positive electrode. So the electrons are there going to flow from the oxidation process, where we have Zn going to Zn2 plus 2 electrons, moving up through the conductive electrode, through the globe or the voltmeter that we've put into the circuit, down and through into the copper. These excess electrons will now cause the reduction of the copper from Cu2 plus to Cu solid. So Zn2 plus and Zn are a conjugate redox pair. Cu2 plus and Cu are another conjugate redox pair, and we have separated those two into the two half cells. Okay. The other thing that we have here is the salt bridge. The salt bridge is required to complete the circuit, so it completes the circuit. It is loaded with aqueous ions, generally potassium nitrate, because they're highly soluble. As the positive ions of copper are sucked out of the cathode half cell, potassium ions will come back down from the salt bridge to balance out that charge. So if I'm reducing copper from copper 2 plus to copper, I will get 2 plus worth of potassium down into that half cell to balance out the charge to 0. On the oxidation side, I'm going to have my negative ions. The anions are going to move towards the anode. And this is because as the solution builds up Zn2 plus, we need to balance that out with anions from the salt bridge in order to keep the net charge 0. If charge builds up in these half cells, we won't see the electrons moving through. Okay, if I build up positive charge in my oxidation half cell, the negative electrons are going to be drawn to the solution. They're not going to be drawn out and over to the cathode, and vice versa. So the key thing for this is to know the components of the electrochemical cell and the definitions of each one of them. The electrode must be an electronic conductor, so it needs to be a material where there are delocalized electrons present, where they can move through the circuit. This could be any metal, or we could use graphite as an inert electrode, i.e. it won't react with anything in the solution, but it still has delocalized electrons to be able to pass that current through. The electrolyte, which is a solution that contains ions, these are usually aqueous solution of copper sulfate or something like that. Typically, we want something where the anions or the counterions won't react with other things in the cell and cause precipitates, because that will cause problems with the cell operation. Half cells contain the separate oxidation and reduction processes within a galvanic cell. So each half cell must contain an electrode that is in contact with the electrolyte and the species present in each half cell to produce a redox pair. So each half cell contains one redox pair for the reaction, okay, and the electrode needs to come into contact with the electrolyte for those redox pairs to be able to react. The internal circuit is the connection formed between the two half cells by the salt bridge, closing up that circuit. The external circuit is a circuit formed via the connection of the anode and cathode, usually with a wire, and typically we put a voltmeter in that circuit or a globe or something like that. The cathode for a galvanic cell is the positive electrode, and it is the electrochemical cell where the reduction occurs. So reduction always occurs at the cathode, and we can remember that by remembering the mnemonic red cat. The anode is the electrode of the electrochemical cell where oxidation occurs. So these two definitions always apply, regardless of the cell we're looking at, being it a fuel cell, a galvanic cell, an electrolytic cell, any electrochemical cell, reduction will always occur at the cathode and oxidation always occurs at the anode. In the case of a galvanic cell or a voltaic cell, the cathode is positive and the anode is negative. The salt bridge is a conductor that connects the solutions and completes the circuit and keeps the net charge in each half cell 0. This means that cations will move towards the cathode and anions will move towards the anode. So that salt bridge provides ions that keep the net charge of each half cell neutral so that we don't get a buildup of charge in either of the cells. And then we do need to be able to label where the cations from the salt bridge will move towards and where the anions will move towards. Remembering in an aqueous solution, the ions are what are conducting our current, and they are readily able to flow through solution. So I will leave you with this. You can cut and paste the link and have a look at how this works. Actually, let's just play it here. Let's see if we can play it here. Then you can watch this cell here. So this again is the Daniell cell. We have the zinc half cell. Our more reactive metal is the anode, and our less reactive metal is the cathode. So you can see the zinc ions form zinc 2+. The 2 electrons pass through the circuit, combine with the copper in the reduction half equation. And we can see the ions, the potassium coming through one side and to the other. That's all I have for redox. Have a go at looking at the different redox reactions. In the next video, we will talk about how we predict which is the anode and which is the cathode when talking about our galvanic cells.